go. So it is the top of the hour, and while we'll still have likely additional folks joining us, I want to get us started because we have a lot to cover today, and we're so excited to have all of you with us. My name is Paige Graff, and I am facilitating today's session, but we have other facilitators on the line, such as Suzanne Foxworth and Rosina Miller and Kim Willis, who's watching in the background as well. So we're so glad that we can be here with all of you. We want to officially welcome all the participants that are joining us today. As you can see from this map, we have folks from all over the United States as well as 4 countries. And we have a range of folks who are students in classrooms, to educators, to college level students, to museum folks, librarian folks. We welcome all of you to our webinar today. We're so excited to have all of you with us as we talk about To Bennu and Back, preparing for OSIRIS-REx sample delivery and curation. Today's session will run for about an hour plus an additional 15 minutes for Q&A. So if you have questions, by all means, put those questions in that Q&A area if you are on the live session. Now, I also want to take a brief moment, of course, to welcome our speakers. Our speakers are very busy individuals who have graciously taken time out of their schedules to be able to share some important and exciting content with all of you. We have Paul Abell, Maritza Montoya, and Julia Plummer. Here's just a little bit about them so you have an idea of their background. Well, Paul, he's NASA Johnson Space Center's chief scientist for small body exploration. He's originally from Manitoba, Canada, and he has a bachelor's in astronomy and physics from Colgate University, a master's in space studies with a geology minor from the University of North Dakota, and a PhD in geology from Rensselaer Polytechnic Institute. He's been at JSC for almost 20 years. Now, Maritza Montoya, she's originally from Houston, Texas, so she's a local. And she has a bachelor's in geology from the University of Houston, and she has a master's in progress, also from the University of Houston, in geology. She is a small particles processor and has been part of ARES for about 2 years now. And last but not least, Julia Plummer. She's also originally from Houston, Texas, and she is a Bachelor of Geology from Texas A&M University. She's also a small particles processor and has also been a part of ARES for approximately the last 2 years. Now, both Julia and Maritza support Hayabusa 2, a Japanese-led mission to an asteroid, and OSIRIS-REx curation activities in support of global scientific community investigating the origins of our solar system through studies of samples from asteroids Ryugu and Bennu. So Julia and Maritza, they get their hands-on. They never touch the samples, but they use the proper equipment to work with those samples, and they're part of today's presentation, sharing their exciting wait for these samples. Will round out what we'll learn from Paul and what OSIRIS-REx is all about. So again, we welcome all of you to our session today. Use that chat for any responses to some of our scientists' questions and Q&A for any questions that you have. So with that, I'm going to stop sharing and I'm going to turn things over to Paul to start letting us know a little bit of background about OSIRIS-REx. So Paul, over to you.
Hey everyone, good morning, good afternoon, wherever you are. I'm going to be giving you a little bit about the OSIRIS-REx mission overview. We're really excited. I can't tell you how excited we are for this spacecraft to actually deliver the samples back. So my name is Paul. I'm the chief scientist for small body exploration. Basically, I do a lot of asteroid work. Near-Earth asteroids are my specialty. But let's get right into it and talk a little bit about OSIRIS-REx. Okay, so OSIRIS-REx, it's a acronym, stands for Origins, Spectral Interpretation, Resource Identification, Security, Regolith Explorer. That's a mouthful, but over here on the left-hand side is the acronym. I show you a picture there of the spacecraft. In front of it is the mission principals investigator, Dante Loretta. And he's super happy because this is just before the spacecraft is going to be put inside that nose cone you can see there in the back and then attached to the rocket. So why OSIRIS-REx? So origins, want to know where we came from. These asteroids are thought to influence how life evolved on the Earth and how the planet may have formed itself. Spectral interpretation, what is actually out there? What type of things are out there in the asteroid belt? Resource identification, can we use the materials from asteroids? Can they be useful to us back here on Earth or maybe actually in space? And then security, some of these asteroids, as you know, can give us a bad day. We don't want to end up like the dinosaurs. So can we prevent an impact if we see an asteroid coming at us? That's another part of the mission. And then Regolith Explorer, that's the part, the surface that we're bringing back, the samples that we're bringing back. So let's bring that sample home and let's learn everything there is to know about OSIRIS from Bennu and OSIRIS-REx, okay? So a little bit about how the asteroid Bennu was chosen. There's over 500,000 asteroids in the main belt, and I'll go into that a little bit in the next couple of slides. Over 7,000 of those are near-Earth asteroids. 192 at the time of the mission that was looked at had good orbits for sample return. In other words, getting there and back. We also wanted an asteroid that was quite large, bigger than 200 meters, so twice 2 football field size, right? There's only 26 of those. And then we're also looking for carbon rich, 5 of those. And that last one, the best one, was Bennu. So basically, it had to be close to Earth, good orbit, and a good size. Bennu looks to be primitive, carbon rich, looks like it may have lots of organics, maybe even some water inside the clay minerals that's on its surface. And if we do find organic molecules on there, they may have been very similar to some of the molecules that came to Earth. So they may have, learning about Bennu may actually help us learn about how Earth formed, as I mentioned before. So that's how Bennu was chosen. All right, so a little bit about asteroids. Here's our great planet Earth. We're gonna drop it in on the solar system. You're looking down, the yellow dot is the sun. We've got Mercury, Venus, Earth, Mars is that red dot. The asteroid belt is that gray band around, and it's between Mars and Jupiter. Jupiter's that last, the yellow dot, the outside ring there, okay? So basically, asteroids are rocky leftovers of the planet formation, right? So when the solar system formed, we had lots and lots of asteroids. They all formed the planets and the sun, but what was left over formed the asteroid belt. There are lots and lots of asteroids out there, but there's not enough in terms of mass to even make our moon. So on the lower right, I show an animation here of the inner part of the solar system. That green cloud, those are all main belt asteroids, but the red and orange dots, those are near-Earth asteroids, of which Bennu is one. So near-Earth asteroids come from main asteroid belt as those asteroids collide and send asteroids inward towards the solar system. Those are near-Earth asteroids because they come near to Earth. So here we go. Here's Earth. Here's the moon. Here's Ceres. Ceres used to be the biggest asteroid in the asteroid belt, but it's now a dwarf planet. But this is just to give you a sense of scale. These are now images. These are all images of asteroids that have been taken with spacecraft, right? All of these except one are main belt asteroids. So on the right-hand side, we have Ceres, like I mentioned. It's about 1,000 kilometers across. It's about the size of Texas. For Vesta on the left is about 500 kilometers across. And then you can see all these other main belt asteroids down there, and they get, they're still pretty large. Some of them are tens of kilometers long. And then that little dot right on the bottom is Itokawa. That was the first near-Earth asteroid that the sample was obtained from by a Japanese Hayabusa mission. That's about 300 meters, okay? So here's what we knew about Bennu. This is what we had from Earth. So just basically before, just using our telescopes, looking at Bennu, We had some radar information, we had some infrared information, some telescope information. Basically looked to be about 500 meters, so that was a nice size. Looks like it's sort of like a roundish spinning top. It's not rotating very quickly, so it's about 4 hours rotation period, a little over 4 hours. So that's pretty good. So that makes it like easier to land on. And more importantly, the surface of it was thought to contain small particles like a sandy beach, at least in some of the areas. So that's important if we're wanting to try and get a sample. On the right-hand side here, you can see the diagram, and you see that green line, that green circle, that's Earth's orbit. The blue line is Bennu's orbit, and you can see why this is one, a near-Earth asteroid, but also why this makes it as an attractive target for us to go rendezvous with it, study it, and then land and then bring samples back. So that's just to give you an idea. All right, so how tall is asteroid Bennu? Asteroid Bennu is about 510, 500 meters in diameter. There's the Empire State Building and the Eiffel Tower to scale. So this is a pretty big asteroid. Keep in mind, though, it's not as big as Ceres or Vesta, but it's still pretty big. And of course, something like this, we would not want to hit the Earth. But again, for our purposes, this is the asteroid we're going to and bringing samples back to learn about the wonders of the solar system. All right, when we do these type of missions, these sample return missions, these spacecraft missions take a long time. So here's a mission timeline, and I've highlighted some text in red here for key dates of when we decided to do the mission. So it was way back when it was selected in 2011, 2016 launch, 2020 was the arrival, and then we're looking forward to the return just in less than a couple weeks, September 24th, 2023, and then the mission doesn't actually end until the sample analysis is finished, which is in 2025. So you can see this type of mission, they take a long time, so 14 years. So that's why we're so excited to get these samples back. And I know my colleagues, Julia and Maritza, are really, really happy and excited to get these samples back because it's been a while. And we are waiting almost excitedly like Christmas Day for our present to come back. And let's see what we get when we open up that box. All right, so here's the spacecraft. It gives you a sense of how big it is. You notice the people all working around it. This is at Kennedy Space Center. This is, again, getting it ready to be put into the nose cone of the Atlas rocket. It's pretty big. It's, in terms of the solar panels, it's about 20, a little over 20 feet long. The width is 8 feet and the height is 10, a little over 10 feet. So it's about the size of a 15-passenger van, right? Just to give you a sense of scale. And that's important later on when I talk about how close we have to get to Bennu and where we have to get to land on Bennu safely. The weight is about almost just under 2,000 pounds without fuel. Okay, so it gives you a sense of how big it is, how heavy it is, and that has to go all the way there and come back to Earth. Here are the instruments, just some instruments for you. Here is on letter A. Hopefully you can see my mouse, but basically we've got the touch and go sampling mechanism. So you'll see that that's where all the action happens. You'll see that in a video here in a bit. We've got some spectrometers, infrared spectrometers, thermal emission instruments, and cameras all in the front in this part here, where the spacecraft uses those to characterize the asteroid, figure out all the hazards that may be there, but also where we want to go for sample. We want to study the asteroid, and you'll see that in some of the slides I have later on, but really important to get a good characterization of where we're going. Also, we've got an X-ray spectrometer. This part here, this white thing, this is the sample return capsule that's coming back. That's the thing that's going to come back, and you'll see that. Here's the high gain antenna here, and then we have a laser altimeter. Basically, that's like sending a laser beam to help find the range or the distance to and from the spacecraft from the asteroid surface. So this is a big instrument suite, but all of this, all these instruments are basically designed to make sure that this white sample return capsule makes it back to Earth. That's the main objective of this mission, is to return a sample safely and bring it back to Earth. Okay, and now I'm going to show you a video of the launch. So I'll be quiet, it'll have animation, and just enjoy.
Status check to proceed with terminal count. Atlas systems, propulsion.
Go.
Hydraulics.
Go.
Pneumatics.
Go.
LO2.
Go.
Vehicle system engineer.
Go.
Anomaly chief.
AC is go.
Range coordinator.
Clear to proceed.
Launch director.
LD is go, and you have permission to launch.
Proceeding with the count. Status check.
Go, Atlas.
Go Centaur.
Go OSIRIS-REx.
5, 4, 3, 2, 1. And liftoff of OSIRIS-REx, its 7-year mission to boldly go to the asteroid Bennu and back.
Bearings look good. Calculating pump speeds and turbo pressure short of 10. Screen chamber pressure set plateau without ramp. Program is complete.
And you see the solid rocket booster jettison.
Separation looks good. Yeah, full thrust on the aero fin. And we have indication of spacecraft separation.
Okay, so that was the launch. Now we're on our way. So here's an animation. I'm going to talk you through this. So here's OSIRIS-REx arriving at Bennu. Again, this is a computer animation, so this is not exactly real imagery. First thing we want to do is map out the asteroid in its entirety, trying to figure out what it's like, what its special features are, and then trying to look at sample sites. Once we have some sample sites, we look at those up close and personal in more detail, and we choose those for our sampling. So remember I said the sample acquisition, the TAG-SAM, it's the touch and go sample acquisition mechanism. It's on a long arm. It's about 11 feet long, that's deployed from the spacecraft, and it has a TAG-SAM head, that little head that's about half a meter across in diameter. And basically that is the surface that touches down on the asteroid. Now you'll notice that OSIRIS-REx has oriented its panels. They've lifted the panels up slightly. That's to help them maintain safety, make sure there's not a lot of debris that's flown back on the solar panels. And you'll see now the moment of touchdown. Here is an image of the practice in a microgravity airplane, but this is how the sample mechanism works. Nitrogen gas is ejected into the surface of the asteroid, and little bits of the material, the regolith, are trapped in that outer ring as the gas goes through. So that's the moment of touchdown in terms of the artist's impression. Basically, OSIRIS-REx backs away. The sample TAG-SAM head is stowed in the sample return capsule, or SRC, and then detached from the arm, and then the sample return capsule lid is closed. Okay, so that's just to give you an overview idea of the mission up to that point. And of course, this has already happened. That maneuver had already happened on October 20th in 2020. All right, so these are real images now. These aren't artist interpretations, but this is the image. This is one of the first images that from the spacecraft was obtained on August 17th, 2018, about 2 million kilometers away. This is the first image of the asteroid Bennu. OSIRIS-REx is approaching it, right? Now we're getting a bit closer, a lot closer. Actually, that caption is a little bit wrong, but anyway, there we're getting a little bit more detail. And then this is the full view of Bennu as we get up close and personal. So now we're about 50 miles, 80 kilometers away from Bennu. And you can see it rotating, and it's really, really interesting, right? So now we looked at this asteroid for a long period of time, and we mapped all of the asteroids as much as we possibly could, almost all of it. And we made lots of interesting observations. So I have a question for you all. What observations can you make about Bennu? List those observations in the chat. And Paige, I'll turn it over to you.
Great. Thanks, Paul. So for folks in the chat, again, if you want to give us a little bit of what group you're with, Solar System Ambassador from whatever state or your school name, that will enable us to give you all a shout out if you'd like. So we did get some input that's coming in, and others, as you're looking at this rotating Bennu, you're perhaps making your observations and sharing with us. So we did have a solar system ambassador indicate it looks like a rubble pile. We had another solar system ambassador say it's like the predicted shape. We had a solar system ambassador in Florida say like not a sandy beach, but very rocky. We've had Clark High School mentioning they see some craters. One of our solar system ambassadors is mentioning that Bennu seems to have a lot of boulders scattered all over its surface. Duxbury Senior Center in Massachusetts said it looks like a bunch of rubble, like a rubble pile. Our planetarium coordinator from Mesa says there's a few dark spots among the mostly lighter colored material. So looking at sort of the coloration. Another solar system ambassador says a big chunk in the southern hemisphere. Also from Utah, solar system ambassadors mentioning different reflective sections. Menominee High School said bumpy, not round, diamond-shaped, light and dark patches, boulders. Nice, concise, direct observations there. We've got another individual saying that it seems wider near in that sort of equator region. So we've got a lot of really interesting observations. Someone else has added in, one of our solar system ambassadors, that it seems to present somewhat of a challenging surface to choose a safe landing spot, perhaps due to all those boulders that many have identified. So, Paul, what do you think of those observations made?
Hey guys, those are amazing observations. That's just tremendous. Yeah, everything that you had said, everyone has said is exactly right, right? Bennu gave us lots of surprises. And it's lots of interesting things in there. We can see craters, we see boulders for sure. We see lots of light and dark patches. So Bennu is a very interesting object and quite a bit different than what we had anticipated from the ground. Like there's no smooth areas, right? So that leads me into the next slide is, it's boulders and boulders and more boulders. I remember distinctly that, from the first time we got some of the images up close and personal, a lot of people on the team are like, oh boy, we're in for a challenge, right? Some of these boulders are as big as very large buildings, cars. You just look at this image here and you can see all the boulders around. I've highlighted that one that's about 7.5 meters across. Really challenging to find a place where you can put a spacecraft down and get a nice sample, right? So we definitely had our work cut out for us when we looked at this asteroid. We're like, okay, we got to figure things out. We got to do things a little bit differently. But that's the nice thing about space exploration. If we knew everything, it would be pretty boring. And it's always nice to go out there and find new surprises and now start to ask even more interesting questions about what is out there. So choosing the sampling site, right? So there's four main things when we choose a sampling site that we have to consider, right? The first one is deliverability. We've got to be able to get in there into the sample site easily and get in and out, right? We also have to have safety. When the touch and go sample acquisition mechanism, or TAG-SAM, head contacts the surface, the spacecraft can't take any damage, right? Because remember, we're trying to get the sample, we're trying to get down there and bring the sample back to Earth. So any damage to the spacecraft, that would jeopardize the mission. So we have to be able to get in there easily, get there safely, but also we have to be able to sample effectively, right? So the sample site for this technique that we used with the TAG-SAM head, putting nitrogen gas into the asteroid surface and picking up small particles, they had to be 2 centimeters or smaller, right? So it had to have that type of sample size that we could see before we would have confidence that we'd be able to collect a sample effectively. And then the last thing is science value. We really need to have pristine regolith with carbon-rich, diverse, primitive materials and even hydrated materials. So we'd have to learn about the surface. That's why we spent so much time mapping out the asteroid, finding out where all the hazards are, where it was safe to go, how big the particle sizes were in those areas, and then what type of particles were there, because we were after these carbon-rich, primitive, and hydrated materials. So here are the sampling sites that we actually came up with. Whenever we do things at NASA, we always like to have some choices, right? So here's the asteroid, here's Osprey, Kingfisher, Sandpiper, and Nightingale. Those are the four sampling sites that we chose based on the criteria, those four things that I mentioned in the previous slide, right? So here's another question. So here are these sampling sites, right? Nightingale, Kingfisher, Osprey, Sandpiper. These are what the sampling sites look like. They all are, good from the standpoint of the criteria that we need. But here's a question for you. Which sample site would you choose as the primary sample site and why? Remember that we always pick one sampling site. We do have a backup, but put your answers in the chat. What do you think is the primary sample site?
And again, let us know a little bit about your affiliation if you wish. And if you're thinking, what's your primary sample site, you may also be thinking what site you wouldn't choose and perhaps why. So whatever seems useful, and the why is so much more important than just what's the name of the site. So think about that why. So we did have a solar system ambassador from Florida say Nightingale seems to be the smoothest. Another solar system ambassador from Indiana says Osprey seems to have a large flat area. Kingfisher looks a little bit too rocky. Another solar system ambassador says Nightingale looks like darker, maybe carbon rich or volatiles in that particular site. Duxbury Senior Center in Massachusetts says, I think the best is Osprey. It seems to be the most open. So thinking about that safety value. Another individual is mentioning from Rose Holman that Nightingale, I wouldn't because there seems to be a large rock that you could hit. So they don't like the idea of Nightingale, doesn't look safe enough. Sandpiper appears to be flat and level from a solar system ambassador. Another solar system ambassador says Osprey had to get to the central dark spot and it looks pretty open. Menominee High School says Osprey, the crater might make it easier to sample along with fewer craters in the area. Love these responses, by the way. We have another solar system ambassador who is mentioning Osprey because of the recessed area that could perhaps accommodate the TAG-SAM's arm collection. Monsanto Middle says Osprey because the terrain seems a bit more open, more open to obtain a sample. Clark High School is indicating between osprey and sandpiper, since they seem to have a variety of rocks that perhaps could be gathered. Mid-South Gifted Academy says they think sandpiper because of lots of small rocks, more diversity of samples, and it looks a bit more flat, which might be good for safety reasons. So we've got a little bit of everything. Some we wouldn't go here, some we would go here. What do you say, Paul?
Hey guys, I really like the way you're thinking. This is exactly what we went through, in the team when we're trying to pick our sampling sites. So it's exact same type of things. All the discussion here, it's really, really good. It was a tough decision, but basically this was our primary sample site and this was our backup. So Nightingale was our primary, the sample site was Osprey, right? So the reason we chose Nightingale is in here, so it's a little bit big area. There is that big boulder you'll see down here that we'd have to avoid. The area is only 16 meters across. It's still a tight fit, but when we looked at it and compared to the other sampling sites, Nightingale contains mostly fine-grained dark material, okay? So that means that it has a good chance for collecting sampleability. It also has a chance for getting the high science value. It also has a higher color variation across the surface, which suggests diverse types of materials. So in other words, going there, you may be able to pick up a wide range of material types. So that's why OSIRIS-REx, we went to Nightingale Crater, okay? But I love the way you think, and all those answers were tremendous. So Nightingale is where we did the tag. So here's the tag. This is from October 2020. I'll let this run real quick. There it is, the moment of tag, the gas firing. Lots of debris came up during that. So it was a very surprising. We didn't think it was going to be that energetic. The sample had actually penetrated into the asteroid for about a half a meter. So again, very, very energetic, but hopefully very, very efficient. And we know this because when we brought the sample head back to look at the camera, changed the arm and pointed it back at the cameras of the spacecraft after we moved away from Bennu, we saw this. And you see all those little bits or sample that are leaking from the sample head, and all of that material, there's lots of material in there. So we're like, okay, we need to stow the sample right away so we don't lose any more. But it looks like the sample head is pretty full. So we were excited about that, but we wanted to stow the sample. So the last video I'm going to show is basically the return. So I'll let this play. It has audio, and then we'll go from there.
After arriving in 2018, OSIRIS-REx spent nearly 2 years orbiting Bennu, mapping and studying its rugged terrain before carrying out its primary science objective. On October 20th, 2020, the spacecraft ventured to a small crater in the asteroid's northern hemisphere. It dodged jagged rocks and towering boulders and plunged its arm into the loose surface, excavating 6 tons of debris while collecting about 250 grams of material. OSIRIS-REx stowed its bounty and closed its sample return capsule. It bid farewell to Bennu in May 2021, embarking on a 1.2 billion-mile cruise back to Earth. Now, 2 years and 4 months after leaving Bennu, OSIRIS-REx is closing in on the place where its journey began. On September 24th, the spacecraft will approach to nearly 63,000 miles from Earth. It will power up and release its sample return capsule at 4:42 a.m. Mountain Time. The capsule must be jettisoned within a narrow time frame and at just the right angle to hit its target, an area of roughly 250 square miles in Utah's West Desert. Once the capsule is away, OSIRIS-REx will fire its thrusters to avoid colliding with Earth. At 8:42 a.m., the capsule will streak into the atmosphere at a blistering 27,000 miles per hour. It will race across the western U.S. and begin to glow with heat, allowing infrared trackers on the ground to chart its progress. As it pushes deeper into the atmosphere, the capsule will rapidly decelerate, subjecting the Bennu samples to a punishing 32 Gs. About 2 minutes after entry, it will slow to Mach 1.4 and deploy its drogue parachute, stabilizing its descent. The capsule will enter special use airspace at 8:46 a.m., almost 10 miles above the Department of Defense Utah Test and Training Range. Radar stations will lock on and track it to within 30 feet of its landing site. At 8:50 a.m., the capsule will extract and deploy its main parachute 1 mile above the ground. It will make its final descent at a leisurely 11 miles per hour, like a marathon runner savoring a victory lap, before touching down in the desert soil at 8:55.
And there we have it. So I'm gonna stop sharing and I'm gonna turn it over to Maritza and Julia.
On September 24th, the capsule will enter Earth's atmosphere at 10:42 a.m. Eastern Time. After it enters the atmosphere, about 13 minutes after, it'll land on the Utah Test and Training Range, and 1 mile above the desert, the parachute will deploy. On the top photo is an image of that. And it will slow to about 11 miles per hour before landing. So there's a recovery team that will go out and examine and prepare the capsule for transportation to a temporary clean room. And on the bottom photo, you can see we have one of our Lockheed Martin technicians checking the temperature of the capsule to make sure that it is safe for the team to come and inspect it. So I have a question. Let's see. How do you think the capsule will be transported to the temporary clean room?
So as you think about this, you can see the size of that capsule landing in the desert, and in that relatively close area, a little far away, how's it going to get transported? So let's see what folks in the chat have to say about how they think this return capsule is going to be moved to this temporary clean room that you'll hear a little bit more about in a little bit. How do they get it to its next location? So as we get any input coming in, again, let us know if you would like your affiliation. Now, Menominee High School says maybe a pickup truck handled with gloves. One of our solar system panelists or solar system ambassadors says maybe bubble wrap it in a box and then transport it with a truck. One of our other solar system ambassadors says a sealed special purpose van. A couple of our other solar system ambassadors have said maybe a helicopter would be their choice, as I think that's also Quest Academy also says maybe a helicopter. So I love the interesting bubble wrap box and then a truck. Mid-South Gifted Academy says protected transport or a helicopter. Our solar system ambassador in San Diego says a truck to be able to transport it. Monsanto Middle School says it could be transported by train and or by a large truck. So we've got a lot of folks thinking, and I can absolutely understand, a large truck seems to make sense, or some of these other options, a helicopter or the bubble wrap box and a truck. So Julia, can you share a little bit? What are your thoughts and how are we going to transport it to the temporary clean room?
Yeah, so those are all great answers. So we'll actually transport the capsule via helicopter. So the canister will be wrapped in Teflon and a tarp and in a cargo net, and they'll use a long line to transport the capsule to a temporary clean room on the military range. So the goal is to get the capsule from the field to the clean room within 2 hours. From there, it will go to the temporary clean room and undergo initial processing and disassembly to be put on a nitrogen purge. So the top right photo, you can see that is the actual temporary clean room in the hangar at Utah. And the bottom two photos show Lockheed Martin technicians. They're working on disassembling the canister, and Lockheed Martin, Colorado is one of our rehearsals. So they'll be suited up just like what you see in those bottom two photos in that temporary clean room on actual sample return. So we put samples on a nitrogen purge to protect them and keep them dry and free from oxidation. So Maritza and I both have roles at UTTR. One of my roles is to brush off the capsule before it enters the clean room. When it comes from the field, there's a high chance that it'll be muddy and kind of dirty, and we don't want that to go into the clean room. So I will be scraping off kind of like the bottom where you see the white of the capsule, and we'll collect those samples and take them back to JSC. I'm also part of a team that bags, photographs, and enters items into the database as items are being removed from the capsule during disassembly from the clean room. So those items will be also shipped back to here in Houston for our database and collection. I'm also part of an off-nominal sample collection team. So if there is a hard landing and the samples are breached and they're scattered on the desert, I will be one of the processors that goes out and helps collect sample and try to help preserve it. You want to go over your roles?
Yeah, sure. And so for UTTR, this is Maritza speaking. I will be part of videotaping, video documenting everything going out outside of the clean room at UTTR. Below is a photo of myself outside of a clean room at Johnson Space Center. That's not very accurate. It's really difficult to share photos from a military base, so we don't really have one of me recording at the clean room. Also, apart from that, I'm also on off-nominal sample collection, just like Julia. We are all prepared to be each other's backups, and in case that none of us are able to make our role. So in case one of us is sick, we all have learned each other's role. We know exactly what each process is. We've gone through many of the procedures. Another thing that I do that I didn't list it is media. So if I have to talk to a news reporter, whether that be in English or Spanish, I am prepared to do that with the training that I've completed.
Yeah, and so I can go over that photo on the bottom left. So you're probably wondering why we're wearing white bunny suits and face masks around the capsule. It's because a lot of us have backup roles. So I'm a backup role for inside of the clean room. And to go into the clean room, you have to be clean. So the white bunny suits kind of helps protect us from getting dirty, and the face masks are just to help keep us safe from any outgassing that might be happening on the capsule. And the heat shield will be very charred and dirty. So after capsule disassembly, the canister that was enclosed inside of the capsule would be bagged and stored in a shipping container on a nitrogen purge overnight. So the left photo, it's kind of hard to tell, but that is how the canister looks enclosed inside of the canister or the capsule. And then the middle photo shows the middle photo is the capsule that was inside of the canister. So you can see it's sitting on the table there, and that will actually go on a nitrogen purge. And the samples are, the taxam is contained inside of that capsule. So the canister will be transported to Houston the following day on Monday, September 25th. And how do you think the samples will be transported back to NASA Johnson Space Center in Houston?
Great. So remember, the sample is currently, at least in these pictures, in Utah. So how are they going to get it from Utah to Houston? And we'll see what type of answers we get in the chat. And again, if you want to give us a little bit of your affiliation, that would be great. So our San Diego Solar System Ambassador says probably an aircraft. Duxbury Senior Center says by plane. Now, regular plane like Southwest Airlines or United Airlines, or perhaps some other type of plane. One of our other solar system ambassadors from Indiana says maybe a military transport plane. Another solar system ambassador says a special purpose NASA aircraft. Mid-South Gifted Academy says some type of jet. Menominee High School is thinking maybe a truck or perhaps a special plane. Clark High School is thinking perhaps some type of jet as well, especially thinking that we've got to go from landing on the 24th in Utah to somehow getting to the Johnson Space Center in Houston the very next day on the 25th. So most are saying some type of plane or perhaps a truck. Nobody said a helicopter. So Julia, Maritza, how is it going to get to space to Houston?
Yeah, so those are great answers. It will actually be transported on a C-17 aircraft, and it'll land in Ellington, which is about 20 minutes from NASA. So Maritza and I will actually be riding back with the samples to Ellington, so we're very excited, and we'll be getting right to work on Tuesday to help disassemble the tag stamp. And I'll go ahead and turn it over to Maritza, and she'll talk about the clean room.
So in our clean room spaces here at the Johnson Space Center, we have an ISO 5 clean room ready for our samples. We have 2 glove boxes in our clean room, and we have a glove box for each major disassembly portion of our procedure. You can see the labeled glove box in the front, which is the TagSam glove box that's nearest to the image on the left. And this is where we will disassemble the TagSam itself. And again, the TagSam is what touched the surface of Bennu and has a sample collected in there. But before we could even get to the TagSam, we first have to remove the sample return canister, which it's inside of. And on the right, you can see the glove box on the back, and that's where we will be first putting it in. I kind of started that a little bit backwards, but that's okay. So the picture on the right is where the TagSam is supposed to come in inside of the sample return canister. From there, it gets transferred to the glove box on the right. And so these are 2 major different processes occurring, 2 different glove boxes that we have been practicing in. Next slide, please. Okay, so a little bit about the hardware deintegration process of inside these glove boxes. We have rehearsals that we do together as a team. We have OSIRIS scientists and other engineers training in laboratories, and we have things called dirty rehearsal spaces and also clean room spaces. In the photos here, we're actually in our clean rooms. On the leftmost image is myself. We do training in other laboratories. So this is a laboratory where all the Antarctic meteorites get transferred to Johnson Space Center, and they allow us to go into their glove boxes and practice with a 3D printed version of our TagSam. And these are trainings that all of the processors have had to complete. The image right next to that one is Julia and myself standing in a clean room bunny suit. We have to wear these bunny suits that cover us from head to toe. And in this photo, we're not taking anything apart. We're actually reassembling the TagSam. So if you think of a Lego set, you're putting together a Lego set. This is kind of what we're doing. We're putting together our TagSam for another rehearsal, another practice is what we're doing. The big image is a blown up of all the processors on our team. This is not the whole Curation team. We are made of many engineers, many processors, many scientists, and including technicians. Everyone it's taken a big village to get ready here at the NASA Johnson Space Center for receiving OSIRIS. Next slide, please. This is small handling practice. So Julia and I are small particles processors. When we first arrived at JSC, our first training was to learn how to handle very small particles at the micron scale. In the image on the far left, you can see our Hayabusa 2 curator and small particles lead, Christopher Sneed. He's leading a training, and we are learning how to remove very tiny rock fragments. And this is not the real thing, right? This is just a replica of what we're expecting to receive. And we're in our dirty rehearsal space. This means that we are not in the clean room. We can wear our regular clothes, and we have these mock-up glove boxes that really are almost copies of what we have in the clean room. In the clean room, it's all stainless steel. It's all clean. And so there's a group of us around Christopher, and we are seeing how he's extracting very tall to small rock fragments with a pair of tweezers. We are also trying to figure out which tweezers are the best. Do we like the bent tweezers that are a little bit bent, or do we like the curved tweezers, or do we actually like self-closing tweezers that can close themselves if you squeeze them? So there's a lot of different things. In the middle is Julia. She's also taking a turn. So after our lead shows us how to do something to extract a particle, Julia is coming in, and now she's taking a turn to try to do exactly what he's doing. And in this process, we are all talking together. We are all saying, okay, I like this form better, or I'm left-handed, I prefer this side, but you can move it for yourself because you're right-handed. There's a lot of different conversations happening here. And so the rightmost image is just a zoomed in portion of that sample handling practice that you can see us in those gloves. Next slide, please. And again, this is more of our dirty rehearsal space. This is a sample pour on the far left. On the far left image is a group of people, but at the main processing part is Julia and our another processor, Rachel. And so they are getting ready to practice pouring out some rock fragments that closely resemble kind of what we're expecting from asteroid Bennu. They're pouring it onto a tray system, and you can see it almost looks like this pizza tray that we're pouring it into. And so we are practicing at the bottom middle photo. You can see myself next to our curator, Nicole Lenning, and she's selecting a rock fragment. She says, okay, so this is the rock that the science team wants, because it's a whole team selecting which samples we should get first out of the pour after it's poured onto this tray system. And she's telling me exactly what area I should aim for, what rock they want. And then on the rightmost image at the top is myself grabbing that exact sample for her. And then we'll remove the sample and weigh it, take pictures of it, and containerize it, and give it to the lovely science team members to do their science. Next slide, please. And back to our clean room spaces. This is just showing a different part of our procedure. This is showing us where the different challenges that we have to go through, or to get these samples and to work in these glove boxes, to work in this clean room. It's not the easiest thing to do. When we put on these bunny suits, we are automatically 10 degrees warmer. Our body heat is already, we're sweating probably by the time we're going into the clean room. And we have to wear these bulky gloves. And if you're working with small particles, you have to be very careful. You have to be extra careful because you're not using your hands, your bare hands. And so it's a bit different. Kind of if you're sewing something, when you're sewing something with your bare hands, it's probably easy or difficult. It's already difficult enough as it is on your own. But then add like these big giant covers for your, these big giant gloves, and then try sewing. It's difficult. It's not the easiest thing. And also there's a nitrogen atmosphere in these glove boxes. So there's this positive pressure working against you also when you're working inside of them. In these photos, we are removing contact pads, and those are the little circles around the tag SAM that touch the asteroid. We are practicing containerizing them. You can see Julia and myself. I'm removing the contact pad and I'm passing it to Julia, and she's not only just ready to get the container from me, she's spotting me. And I have other people, other scientists across from me spotting me to make sure that I'm not putting in danger any other sample, or that I didn't drop something. If I do drop something, they're going to be able to catch it, or not catch it, but they're going to be able to see where it dropped. And so it's very important that we are all in sync with one another, that we all know what we're doing in the procedure. And that's a major thing. Next slide, please. And so OSIRIS-REx, it comes back this September 24th, and we have done numerous rehearsals at JSC, at JAXA. This JAXA Curation team has worked tremendously to be ready for OREX, and we're really excited and happy. Thank you all.
Great. So as you can see, oh, was that it, Maritza and Julia?
Yes.
Yes.
Awesome. Well, as you perhaps have seen, there's some intricate work going on there as they are working with that sample. So first step is getting the sample from OSIRIS-REx, which Paul talked about. Next step is getting that safely to land in the Utah desert, which both Paul and Julia Maritza talked about. And then that next step of getting the sample into the lab and working on it, as Julia and Maritza will be doing, that is such an important part of the process. Thank you, Paul and Julia and Maritza, for sharing the work that you've been doing and preparing to be able to get the sample safely to our lab and then out to scientists to be able to study. Now, while we are near the top of the hour, some of you may need to depart here in a minute or so. And if you do, I just want to acknowledge and thank everyone for joining us today. We're so thankful for your participation. We're also so thankful to Paul, Maritza, and Julia for sharing their expertise. And they're willing to stick around for at least an additional 15 minutes to answer many of the questions that you have had come in. So I'm going to get right to questions. And again, if you have to depart, thank you so much for joining us. If you're sticking around, here's some questions. Now, we had some questions that came in with some registrations. So the first one I'll ask actually to Julia and Maritza. So this solar system ambassador from Maine is asking, where is the sample going to go for analysis? Will it stay at the Johnson Space Center? Will it go elsewhere? What's the sort of chain of custody, so to speak?
Right. So we have a lot of different groups working on our team. We have a science analysis team that is composed of many different groups. And so our samples, there will be a preliminary examination period, and some of it will be measured here at the Johnson Space Center, but a lot of it also will be transferred over to different universities and different scientific communities worldwide.
Excellent. And there are quite a few universities, both across the United States, as well as the Canadian and Japanese counterparts that are also part of the team as well. So lots of research to go along with all of that. Here's another question for Julia and Maritza. So Bakersfield College individual has asked, how much of the sample will be saved for analysis by future generation of scientists?
Yeah, so about 3/4 or a majority of the sample is preserved in a special facility outside of NASA or outside of Houston.
Excellent. So for those young folks out there, there's going to be a set of sample for you to be able to study when you become scientists working at the Johnson Space Center as well. And that's something that NASA does do with their missions, is they always save a percentage of sample for future generations, for future technology, and even for future questions that we haven't even thought of asking just yet. So here's a question, and this question is for Paul. Paul, you showed a little bit about what the spacecraft will do next, but is the spacecraft going to orbit around the sun, or where is it going to go? What's it going to visit? Is its name going to stay the same? What's going to happen with the spacecraft once it drops off the sample?
Yeah, so that's a great question. So as I showed in the video, what you noticed at the spacecraft diverted. It deployed the sample return capsule to Earth, but then it fired its thrusters to miss the Earth and diverted. And so OSIRIS-REx is going to be renamed OSIRIS-APEX, which stands for, the APEX stands for Apophis Explorer. And so OSIRIS-REx, or OSIRIS-APEX, is now, it's going to be in orbit about the sun, but it's going to go on a mission to rendezvous with the asteroid Apophis in 2029. So that's when the spacecraft, this asteroid Apophis, makes a very close approach to Earth. OSIRIS-APEX is going to rendezvous with that asteroid just after Earth encounter and study it and trying to learn much more about it. So actually a great question. So the mission itself, the spacecraft, name changes, but it's still got a few more years in which to work. Actually, a lot more years left to work. So we're very excited for this extended, what we call extended phase of the spacecraft's lifetime.
Excellent. And we look forward to that continuation of details about other asteroids in our solar system. Now, related to that, Paul, we had a question come in from one of our solar system ambassadors. Speaking of other asteroids, is there any coordination of the OSIRIS-REx mission with the Psyche mission or the Lucy mission that are also visiting asteroids?
So it's a good question. We don't have any direct collaboration with those two very different spacecraft missions, right? So Lucy's going to the Trojan asteroids, which are in the vicinity of Jupiter and Jupiter's orbit. Those are the asteroids located just traveling in front of and behind, trailing Jupiter's orbit. And then the Psyche mission is going to a main belt asteroid called actually Psyche, which is a metallic asteroid. So Bennu went to OSIRIS-REx went to Bennu, which is a near-Earth asteroid. Again, all the asteroids are related. They're all remnants of the early stages of formation of the solar system. And so we can learn a lot, but each of the scientific questions and investigations is slightly tailored differently. So there's not really a coordinated effort between the missions, but in terms of NASA, we like to think of this as sort of our asteroid autumn, as you will. There are lots of activities going on, so stay tuned. We've got OSIRIS-REx coming back, September 24th, and then launch window for Psyche actually opens on October 5th. So we're very excited for this asteroid autumn. Lots of activities going on in terms of asteroid science and exploration.
Awesome. And Lucy and Psyche will not be getting samples to return back to Earth. They will do remote observations of those asteroids. So it's not very often that we get sample return, but OSIRIS-REx is our latest sample return that, again, we're so excited about. So speaking of samples, here's a question for Maritza and Julia. So Mid-South Gifted Academy, they're wondering, will any of the samples eventually be observed outside of the glove boxes? Can you talk a little bit to that?
Yeah. So the contact pads that are on top of the tag SAM, we have these contact pads, and they're the little circles that you would see spread out in this circle shape, right? And those contact pads will be containerized and removed into one of them can be taken out of the clean room into another different kind of clean room, and there we will probably analyze that first contact pad outside of a glove box and something like that. But it's always going to be in a laboratory space where it's clean and the air is clean and we're not contaminating the sample.
And would you say those contact pads, are they like, for lack of a better description, are they like Velcro pads that sample could stick to? Is that kind of what those
Yes.
contact pads are?
They are Velcro pads, and if you were to put one under the microscope, you would see loops, and these loops capture particles in between them.
And how many contact pads were around the tag, Sam? Do you know that?
Yeah, we have a total of 24.
So 24, and each of those will be delicately removed, as you saw them talking about that. And I have to say, Maritza and Julia, they're oftentimes referred to as the Wonder Twins by folks in our laboratory. They work so well together. They share an office together. They oftentimes do great work together. And as two young emerging scientists that have only been with JSC for about 2 years. These two Wonder Twins have kind of developed a great reputation within our building, within Aries, because they do such great work. Even though they haven't been around for a long time, they're really awesome stars. So all of this detailed work, it's amazing to think 2 years into their work at the Astromaterials Research and Exploration Science, and they're working with materials that are coming back from an asteroid, NASA's first asteroid sample return. It's got to be so exciting for them. It's so exciting for all of us. Okay, let me go back to some of our questions here. Another question for our Wonder Twins. What do scientists anticipate they're going to see with these samples? What might it look like? What might they look like?
So, like some of the images or the videos that you've seen on Paul's presentation of the TAGSAM capturing those rocky materials, we're expecting to see the same kind of those same type of rocks, different sizes, right? We can have anything from dust to particles a little bit bigger than that, and we work with something called Tagish Lake Simulant, which was a special simulant designed and created to represent that same rocky material that's on Bennu that we've been practicing a lot with.
Excellent. Now, I don't know who can answer this, if Maritza and Julia or Paul, but we had a question that came in related to what's the material the return capsule is made of, and how much does it weigh? Maritza and Julia, do you know any of that information?
I think Paul, maybe the expert.
Yeah, I don't know how much the sample return capsule weighs, unfortunately. The material is a ablative heat shield material. It's very similar to the sample return capsules that we've had before. So this is very similar to the Stardust and Genesis sample return capsules, if that gives you an idea. But I'm sorry, I don't off the top of my head know exactly how much the sample return capsule weighs.
Okay, but I'm sure it is light enough that a helicopter can pick it up once they kind of crate it into that little area that they'll kind of scoop it up with and be able to carry it to that clean room. So here's a question related to that C-17 and the transport back to the Johnson Space Center. So Maritza and Julia, you mentioned that you're going to be flying back with the sample. So like, are there seats in this plane? Where does the sample go? How many other people will be on that plane? Can you talk a little bit to that?
Sure. Yeah, so pretty much our whole curation team, except for 2 members, will be flying back with the sample. It's mostly our processing team. So I assume the sample will be sitting on a pallet, tied down to in the middle of the aircraft. And then our seats will actually be on the outer edges, kind of in a row. I guess what you see in movies, a jump seat looking type seats for the aircraft. Do you have anything?
No, I'm just really excited. Yeah. Never been on a plane like that. So we've never been on a plane like that before, and that'll be our first time.
Yeah, we've only seen pictures, so.
Well, that should be very exciting for sure. And I'm sure they're going to strap down not only you all, but that sample as well as it travels to Houston, Texas. And again, how exciting to think about, just getting on a plane to begin with is an exciting thing, but getting on a plane with a sample that just returned from asteroid Bennu has got to be sort of a trip of a lifetime. So here's another question for the group. So let's see, where did that question go? Oh, so one of our individuals is wondering, was the tag SAM when it went to touch down on the surface of Bennu, was that done using AI? Was it pre-programmed, or was there human input during the sample collection? Can any of you talk to that?
Yeah, Paige, I'll talk to that. And I quickly, just the previous question about the weight of the SRC, the sample return capsule, I actually looked up, had to cheat and look at my notes. It's roughly about 45, 46 kilograms. Okay, without the sample. So that gives you a sense of size of why you need several people to lift it, and also a helicopter can easily carry it. Yeah, so the actual maneuvers at the asteroid, keep in mind, even though it's a near-Earth asteroid, we're still very, very far away. The light delay time, you're looking at several minutes or more, and so you can't really joystick, right? So there's not really command human in the loop. So all of this close proximity maneuvers, and especially the tag itself, the touch and go, that sampling is all done autonomously, right? So it's all pre-programmed. The spacecraft is doing all its own thing. It's checking its position. It's making sure it's safe. It's making sure that it touches down and makes sure that the sample head is deployed properly, the tag SAM head is deployed properly, and then the nitrogen gas fires. And then when it has the sense that, hey, things are going well, we've achieved the sample, we've been in contact with the surface for the sufficient amount of time to collect the sample, then it backs away. And it's only when it backs away to a safe location that we can start having humans in the loop again. But all of that maneuver, all that close proximity, all that sample acquisition, that was all done autonomously by the spacecraft. So very good question.
Excellent. Yeah, and it's so amazing to think about. And Paul, related to that, someone had asked, was there any concern that the tag would alter the orbit of Bennu?
Yeah, no, there's no chance that the tag, that little tag, could alter the orbit of Bennu. It's almost like a very, very, think of it this way, it's the best way. It's not a great analogy, but think of a jet flying and hitting a mosquito. The jet doesn't feel anything. Unfortunately, the mosquito doesn't have a good day, but it's such small amount of force relative to the entire asteroid. The asteroid doesn't even know what's going on, and so it doesn't change the orbit whatsoever.
Awesome. And we've had some great questions, and hopefully we've gotten to just about all of them. I have one last question for each of you, and I'm going to start with Paul, and then we'll go to Julia and Maritza. This particular OSIRIS-REx mission, NASA's first mission bringing back samples from an asteroid. If you could just give us a few moments of what has this mission meant for you, the science you're doing, your career path, what has it meant to you to be involved as a part of this mission? So, Paul, we'll start with you.
So I'll start. I think for me, it's just been a tremendous experience. One of the things that we didn't have time to discuss too much in this video and the slides that we presented is we actually do a lot of international cooperation. We have a lot of partners. I think that Paige mentioned our Japanese partners and our Canadian partners on this mission. But I was actually also helping out with the Hayabusa 2 mission, which is operating almost at the exact same time, and that was a Japanese sample return mission to an asteroid called Ryugu, which is very similar to Bennu. And seeing the cooperation and the collaboration between the Hayabusa 2 team and the OSIRIS-REx team, working out problems, working out how to deal with both of these asteroids, which provided challenges to our sample return strategy. We learned an awful lot, and it was almost like, even though we had two separate missions, we were one big team, and we're actually getting a lot more science from these two asteroids. So I'm terribly excited to see what the samples from Bennu reveal to us. Is it going to be similar to Ryugu? Is it going to be a little bit different? I'm hoping it's different, but let's see. But it's been a rewarding experience, and we can gain so much scientific knowledge through our international collaborations and sharing, and that's why we're exchanging samples between not only the Canadians but also our Japanese partners. So it's just been a tremendous experience, and I can't wait. Can't wait for September 24th.
So this has been an amazing experience for me. Being a geologist, I've always loved rocks and I've always been interested in space. So combining the two has just been my dream job. And I feel so fortunate to be working on OSIRIS-REx with such an amazing team of processors and engineers. And it's just been amazing.
Similar for me, just like Julia, we studied geology in our undergrads. We love rocks. We love rocks and rock formations, like that's our thing. And so when I was in college and, I knew one day that I wanted to work at NASA. That's like a big thing. Like, oh, I want to work with space rocks one day. Like just thinking that in my head, not knowing exactly. I was in high school and not knowing exactly how I was going to get there. But I just knew I wanted to work with space rocks one day. And I was thinking, okay, so maybe Mars samples or maybe lunar samples. I never thought, it never occurred to me that I would be working with near Earth asteroids. And, we handle Hayabusa 2 samples. We're going to handle OSIRIS-REx samples. These are both near Earth asteroids. And it's like a very, it's unbelievable sometimes. Julia and I will be having these pinch me moments of like, is this real? Like, is this really happening? Like, this is so exciting. This is awesome. It's a dream come true. Mm-hmm. And it's not only just for us, right? It's our whole team. We're all excited. Our families are excited. And, the whole country is excited to receive their first ever near-Earth asteroid sample.
And you can hear that excitement in them. I mean, these Wonder Twins and Paul and the whole team. I mean, for those young emerging scientists out there, whether you're in elementary school, middle school, high school, college, or beyond, you never know when that right door is going to open and you're going to find yourself in a place where you're doing something that you could have never imagined. So taking advantage of opportunities, whether they are internships, whether they are ways to try to learn more or get involved. The more you can be involved with things, the more doors can open. And who knows, some of you might be the future Julia and Maritzas and Pauls of the world, because at some point in their careers, they'll eventually retire. But for the time being, I think they've got a good thing going on. And I've said this before in previous webinars, when you love what you do, you'll never work a day in your life. And so our exciting team here with these young Wonder Twins, Maritza and Julia, and they crack up every time folks refer to them at that, but it is true, and they are going to help scientists reveal some additional secrets of our solar system. And like Paul said, with the international collaborations, there'll be so much to learn in the near future, and it will continue for years to come. Well, we are about 20 minutes past the top of the hour. And for those of you that have stuck on the line with us, thank you so much for sticking with us and hearing from Paul, Maritza, and Julia. And for Paul, Maritza, and Julia, thank you so much for joining us today and sharing your knowledge, passion, and expertise about OSIRIS-REx as we wait for the samples to come. Julia and Maritza, they leave for Utah. When do you leave for Utah?
Next Wednesday.
Next Wednesday, and then a few days after that, they'll be in that desert waiting for those samples to return. So we hope you all will join them virtually. I'm sure NASA will have a live feed, and we hope you've gotten some good background about what we're expecting from OSIRIS-REx. So with that, thank you so much for joining us. Thank you again, Paul, Maritza, and Julia, and to everyone, to Bennu and back, and we look forward to great science to come. Thanks, everyone. Have a great day.